just like the binomial, is a discrete distribution. Okay. We're going to go over continuous distributions next, but it's still a discrete distribution. And it's a little different. Binomial was like a pass-fail type distribution. A Poisson is more about the number of occurrences in a certain, typically it's time frame, but something along those lines. The interval. So the book says if X is the number of, the Poisson distribution is used to describe certain events that occur in time or space. That's a good way to think of it. So let X be a random variable that represents the number of events that occur in a time interval of length t. Then X will have the Poisson probability distribution if the following conditions are satisfied. The average rate at which events occur is the same at all times. The numbers of events that occur is non-overlapping. And for very short intervals of length t, it is essentially impossible for more than one event to occur within the time interval. The probability that one event occurs in the interval is approximately equal to lambda times t, where lambda is the average rate at which events occur. And I'll go over that. So first we go over finding lambda and t. Both are going to be important for this Poisson distribution. And I'm going to follow along with the book. It's on page 280. And talks about, it says, the number, this is example 6.18. Says the number of hits on a website during a given time interval has a Poisson distribution. If there are an average of 3 hits per minute, okay, that's going to be lambda. Lambda we know is, I'm going to write this out with units, 3 hits or clicks per minute, right? 3 hits per minute. And X is the number of hits between 230 and 235. So X equals the number of hits between 230 and 235. So we've got a 5-minute window here, right? And that's when you know it's Poisson, because it's talking about intervals, okay? The length of time is, so therefore t equals 5 minutes, right? So if the random variable X has a Poisson distribution with lambda and time t, we can compute probabilities with the following distribution. So it turns out the distribution of the Poisson, now we use capital P, kind of like probability, well, actually it's probability of X, if it's a Poisson distribution, is E raised to the negative lambda times t times that lambda t raised to the x all over x factorial. Okay, this is what the distribution looks like. You've got it in your calculator. I'll help you with that. Actually, my son has my calculator today because he has to take a standardized test. But I'll go over it by hand, and then we'll go over what buttons to press in the calculator on your side, because the phone calculator is different than the actual TI-83. But here's the distribution, which is kind of neat. So if we go back to this example, we get, on average, we have 3 hits per minute on the website. We want to know the probability of the number of hits for 5 minutes, right? So t equals 5 minutes. The question says, this is now on let me use a different piece of paper here. Question example 6.19 follows along with that same information. It says the number of hits on a certain website follows a Poisson distribution where lambda equals 3, and let X be the number of hits in a 2-minute period. A 2-minute, so not a 5-minute, but a 2-minute period. Okay. X is the number of hits in a 2-minute period. It says A, find the probability of 5. Now, what this is actually asking is it wants to know what's the probability there are 5 hits on this website in a 2-minute period. Okay, 5 hits on this website in a 2-minute period, given that we know on average it's 3 hits per minute. So if we plug this into the probability distribution, it's P of 5 equals E raised to the negative 3 times 2. Because remember, our time is 2 minutes, right? A number of hits in a 2-minute period. Times, now lambda is 3. Times again, T is 2. Now we're raising it to 5 here, so because that's the X value, right? I'm kind of following along here. All over 5 factorial. Okay, now E is a button in your calculator. So I can do this part actually. So if we go over to here, click on my calculator. So this is the one on my phone. And I'm going to put this in E. E is, I got to find it. Oh yeah, it's second, I guess, division. Is that right? E. Now we're going to raise it to what? Negative 3 times 2. I'm going to get out of that. And then I'm going to do a parenthesis. So that's the first part, right? Now my phone is kind of janky right here. I dropped it. Negative E raised to negative 3 times 2. And then I'm going to do a parenthesis. Now I'm just going to put in 6 because 3 times 2 is 6. Raised to the 5th power. And then divided by, not times, divided by a 5 factorial. Now 5, and remember factorial, to get that factorial, you do math, and I believe it was probability, yeah, 4. Okay, so you can put that completely into your calculator, and you wind up with 0.606, 0.1606, that is. So this means if the probability that if we know the average number of hits in on this website is 3 hits per minute. Now, excuse me, we're looking at the number of hits in a 2-minute period. So, you know, the average, of course, would be 6 probably. But we want to know what's the probability we have 5 hits in that given period. Okay. Well, that you just plug it into the equation to the distribution in that manner. Okay. Plug it into the distribution in that manner. So let's go over how to do this in your calculator, but I'm just going to go over it from the book. It's on page 283 at the bottom. Okay. So to do this in the calculator, we're going to do the same exact thing and make sure we get the same exact output, okay? To do this in the calculator, you do second vars. Actually, we're not going to do B. This is still A. Second, and then hit the vars button. So we're in our distributions. And if you scroll down, you'll see Poisson PDF. Okay. So hit second distribution, second vars. And then scroll down and you'll see Poisson PDF. Do you have that, Lori? Like, do you have the calculator in front of you?
Yeah, it's
okay.
D.
D, okay.
When you scroll to D.
Option D is Poisson PDF. Now, when you click on that, it'll bring it to the home screen. And if you want to do this example, we actually have, you've got to find, it's the lambda times T. So it's the mean, actually. I know we haven't got to that yet, but it's the mean. So you do the lambda times T, 3 times 2, comma, and then for this one, we wanted to find 5. You put the X value in a 5.
Where's that?
Okay, and that should pop out. Hit enter there, and it should pop out 0.606. Dot, 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 dot. I mean, it's a lot of numbers after that.
2 values 5. Comes out the same.
Perfect. Okay, that's what we needed. Okay, so you don't have to do the equation in your calculator. Or I'm sorry, you don't do the equation by hand really, or put it in and then plug it in and put in your your calculator. You can go straight to those distributions that are built into the TI-83 or 84. Now, if you've got an 83, it tells you how to do that down there as well. It's very similar. Okay, very similar. But for this, really, the hard part's not going to be this part because we kind of get that with the binomial. We kind of understand the aspect of the Poisson. The CDF is the same thing. It's adding it up like the binomial CDF did. So it's going to be recognizing when to use the Poisson. Okay, recognizing when to use the Poisson. So let's look at another example. Let's say we've got
Is that CDF or PDF?
PDF for a single X value.
Which is what we just did?
Yes, ma'am.
Okay.
We'll do one here in a second where we use CDF, okay? Yeah, I'll find one here in a minute because we got to talk about the mean and standard deviation. After that, I'll find one where we use a CDF. Okay, so this is example 6.2 on the bottom of 281. It says yeast cells are suspended in a liquid medium at a concentration of 4 particles per milliliter. I'm going to write that down. 4 particles per milliliter, right? Milliliter. A volume of 2 milliliters is withdrawn. Is withdrawn. Okay. What is the probability that exactly 6 particles are contained in the solution? So I know really I'm going to be finding P of X or P of 6, right? P of 6. Now we've got to find the lambda and the T. Well, the lambda here is going to be 4 because that's the average per milliliter. Okay. And the T, though, I know it's not time here, but it tells us the volume of that's actually withdrawn. So really it's the interval we're looking at is 2 milliliters. So T is going to be 2. So if I wanted to put it in the equation, and I'll do that just for fun, but you can use that calculator, it would be E raised to the negative 4 times 2 times 4 times 2 raised to the 6th power, because our X value is 6, all over 6 factorial. Now, we know we can use this calculator, so it's going to be, in the calculator, it's going to be Poisson PDF, not CDF. And then that parentheses, you do the lambda times T, 4 times 2. You can put in 8 if you want, okay? But 4 times 2, and then our X value, which is 6. And when you do that, both of these should pop out 0.1221. 0.1221, okay? 0.1221.
One, two, two, one.
Did you get that?
Yep.
Like,
It
okay.
worked.
Yeah, hopefully. So let's just talk about a little about the mean and standard deviation. And again, we're not going to really talk about what it means per se. We're going to use that later on in chapter 7, but just how to calculate. It's very, very basic for, actually it's kind of neat for the Poisson. For Poisson, the mean is always just lambda times T. It kind of makes sense. You just multiply lambda times T. But what's crazy, and this is the only distribution that does this, the standard deviation is the exact same, okay? The standard deviation is the exact same. Only time this ever happens. Actually, oh wait, yeah, the variance is the same. I lied. The standard deviation, though, you have to take the square root of it because you have to square root both sides. But the standard deviation is just the square root of the mean. So therefore, the variance is just the mean. Okay, that's not a big deal. You'll see it pop up in the homework where it just asks for it. We're going to talk about interpretations of it later. Okay, it pops up in chapter 7. This is kind of an easy test question, right? What's the mean of this Poisson distribution? Oh, it's just lambda times T. Okay. Let's look at, I'm going to steal an even one. Okay, this is number 20 in your homework. It says the flaws in aluminum foil. The number of flaws in a given area of aluminum foil follows a Poisson distribution with a mean of 3 per square foot. So that's going to be our lambda. 3 flaws per square foot. Okay. Let X represent the number of flaws in 1 square meter. Oh God, of sample. So X is 1 square meter. Now look, we need these to either be in square meters or square feet. These units can't be different. So I'm going to think of, now it's got to be in square meters here. Okay, let's think about this. So if it's going to be in square meters, let's think. This is a good question. Like first it asks for P of 5, right?
Convert the square meters into square feet, like 3 point.
Well, the issue though is that X is given in square meters.
Right.
So it might be that we need to convert lambda into square meters. Yeah, and the like flaws per square meter, not flaws per square feet. Does that make sense?
Yeah.
Yeah.
Either way, you're going to convert something.
You're going to have to convert something. You're exactly right. And because it's giving X in square meters, I assume.
Well, it says for the 3 flaws, it's a square meter, not feet.
Yep. Oh my gosh, it does. Jesus. I read the dang question wrong. I made an assumption. Thank you for reading the question correctly, Lori. Jesus.
You're welcome.
Okay. We don't have to worry about any of that now because now we know that our T is just 1, actually. Our T is 1. I should put it like that. Not X, but our T. Our T is 1. So therefore, if we want to find T of 5, I'm going to just pop it in my calculator. Poisson, PDF, 3 times 1, which is just 3, comma 5. And let me know what you get there when you do that. Okay, let me know when you get there. I've got the answer in my book so I can make sure it's correct. Let me know what you get back.
.1008.
Perfect. That is the answer, 0.1008. So if you want to do it by hand, it'll take you a little longer, but utilize that calculator. It'll give it in 1 step. Now, B says, what's the probability that there's no flaws, right? So we're given this, 1 square meter of aluminum foil, or just aluminum, it's aluminum foil, of aluminum foil. What's the probability that we just don't have a single defect? So Poisson, PDF. It's still 3 times 1, right? Our lambda and our T doesn't change, but our X value now is 0. What's the probability that there's no flaws? This is why it's discrete, guys, is because the X value would be like 1 defect, no defects, 5 defects, right? What'd you get back there?
0.04978.
So 0.0498 if you rounded?
Yeah.
Okay. So look, there's only a 5% or 6% if you round. Well, no, 5% if you rounded. There's only a 5% chance that you would have no defects in a square meter of aluminum foil. Okay, so now here's the question though. What's the probability? And this is where we might use CDF. We'll see. Probability we have less than 2. Probability that we have less than 2. Now remember, PDF adds up from 0 to 1. So if you think of less than 2, this is the probability of 0 plus the probability of 1, right? Now you can add these up. You can do the Poisson PDF for both of those, or you can do Poisson CDF. Okay, and what it will do, now it's still the same lambda and time, but whatever X value is adds up to that X value. Now we want to do 1 here. So what that does, it's going to add the 0 and the 1 together. So help me out. Put in Poisson CDF 3.1 or 3 times, not point, Jesus, 3 times 1, comma 1. And what this is actually it's adding up the probability of 0 plus the probability of 1.
0.1991.
Perfect. Okay. 0.1991. So it just, so the CDF, same lambda and T, but whatever number you put in here, it's adding up discretely to that number. So it always starts with 0. So 0, 1, 2, 3, 4, 5, 6. Well, it wanted less than 2 here, so it's only going to add the 0 and the 1 together.
Which is
Okay.
basically the same as the binom
It's
CDF.
exactly the same. Yeah, exactly the same. Cumulative was the word I was trying to think of yesterday. It's cumulative distribution because it's accumulating as you go from 0. And then part D says, now I've got to use a new page because I ran out. What's the probability it's greater than 1? Now, so really this is probability that our X value is greater than 1. Now, we've got to think of this, though, as the conjugate aspect. The probability that we're greater than 1 would be 1 minus the opposite of this, which is the probability X is less than or equal to 1. We already found, right? So we can do this in the calculator. Look, if you wanted to do the probability that X is greater than 1, you would have to do, I'll kind of do this on the side. You know, greater than 1 would be the probability of 2 plus the probability of 3 defects, right? 4 defects. And you'd have to go forever. Actually, this would go forever, right? You could have, I mean, theoretically, you could have 1,000 defects in a square meter, right? I mean, so we can't add this up the way it's written with this distribution. We have to think of the opposite. So the probability that's greater than 1, oh, that's 1 minus the probability that's less than or equal than 1 to 1. So we already found this from the last question. It was 0.1991. So this winds up being 0.8009. Okay, 0.8009. And then for part F, it just asks, what's the mean? Remember, this is like the easy stuff. Well, this is just lambda times T. So it's just 3. Okay. And then G asks, what's the standard deviation? Well, standard deviation is the square root of lambda times T. The variance is what was the same. So it's just the square root of this, which winds up being 1.7321. Okay, 1.7321. Kind of neat.
Okay, I think you got your F and G backwards. It's supposed to be E and F.
Oh, you're right. Man, what is up with today? Okay, there we go. E and F.
You just want to confuse us.
I am trying to confuse, and you know that's not always a good thing. Okay. Let's see here. Ooh. Let's do 28. It asks the question a little differently, which is kind of interesting. 28 talks about babies born with Down syndrome. It says a report from the Medical College of Georgia stated that the proportion of infants born with Down syndrome is 0.0011. So that's the babies born with Down syndrome, the percent that babies are born with Down syndrome. Proportion. Now, it says assume a sample of 5,000 births is studied. Use a Poisson approximation. Oh, there's an approximation here. Oh, I didn't go over that part. Okay, yeah, Poisson approximation. That's why it looked different. Let's go back now and talk about the Poisson approximation. It's on the bottom of page 282, and then it goes on to 283. It says, when the number of trials in is very large, binomial probabilities can be hard to compute, even with technology, because really this is a binomial distribution. You've got kind of a success fail, right? And we know the probability of success and the probability of fail. And you got 5,000 bursts. This was set up like a binomial. But it says when the number of trials n is large, binomial probabilities can be hard to compute, even with technology. The reason is that when n is large, n factorial is extremely large and will cause most forms of technology to overflow. To be specific, the largest factorial that most forms of technology can handle is 69 factorial. If you try to compute 70 factorial, you'll get an error. Fortunately, when n is large and p is small, the Poisson distribution can be used to approximate the binomial probabilities. The Poisson approximation may be used for any binomial probability with n greater than or equal to 100. Now notice we've got 5,000. Our n is much greater than or equal to 100. So we can use the Poisson approximation on this. And our probability has to be less than or equal to 0.1. Our probability is 0.0011. We are good to go. So it says to compute the Poisson or the probability of X by using Poisson distribution, I use the following steps. Compute P of X by the Poisson distribution with P in place. So RP is 0.011 and our N is 5,000. Well, that actually becomes our lambda and our T, okay? So our lambda and our T, the probability of it success, or for this example, for babies with Down syndrome, that probability becomes your lambda and the N becomes your T, okay? Okay, so this won't be hard at all now. So if we go back to 28, it asks, what's the probability of exactly 5 babies with Down syndrome? So really we want P of 5. So what that means, we're going to use the, not binomial, but Poisson PDF. And we're going to say, it's lambda times T, right? So 0.0011 times 5,000, comma, and then 5. So pop that in your calculator. I can't do this in my calculator. So pop this in your calculator. Tell me what you get back.
Quit turning off. .1714.
Perfect. So I want you to try the next few, knowing what we know here. So that was A. B is less than, probability, we have less than 4. C is more than 3. And then D is the mean. And I can't fit E in here. So we'll do these 3 and then we'll talk about E. So try those 3 now, knowing what we know, when really we're just using lambda for 0.0011, and T is going to be 5,000, okay?
.3575.
Oh, excuse me. No, they didn't get 3575. Oh, okay. Less than, it does say less than 4, right? Fewer than 4, yeah. So this would be, if we did the Poisson CDF, we got to do CDF here.
Right.
And it would be 0.0011 times 5,000, but we're adding it up to 3.
Oh, up to 3. Okay, I did 4.
Yeah,
That's
because
fine.
it's fewer than 4. Let me know what you get there.
0.2016.
Perfect. It would be 1.7 if you rounded.
Yeah.
Yeah. Okay, so more than 3, though, we got to do a little math here. Okay, so that would be the probability. More than 3 would be greater than 3, right? Which would be equal to 1 minus the probability x is less than or equal to 3, which is what we just found. So this would be 1 minus 0.2017, which I mean, I can do this one. It's 0.7938, I believe. Great. Okay. And the mean, which is just lambda times t, so it's just 0.0011 times 5,000. And what this tells us, this mean tells us what we should expect, right? If we have a sample of 5,000, how many babies should we expect to have Down syndrome with, right? And then if you do this, it's 5.5. It's 5.5. So we should see 5. I know that, of course, that's in a way theoretical, right? You're not going to have half. A baby can't have half Down syndrome, but that's just the expectation. That's the expected value is 5.5. So it doesn't have to be a discrete number because it's the mean. It's the expected value. Okay. Okay, do you guys, this section was a lot shorter than I thought it would be. And it's because of binomial. We already went over binomial, which makes it a little easier to grasp in the calculator and the PDF and the CDF stuff. So if you haven't watched that binomial video, you'll see that this one's kind of harder. This one doesn't make as much sense. If you go back and watch 6.2, it makes this discrete aspect a lot really kind of easier to grasp. But are there any questions? I'm going to give you the homework for 6.3. It's not that much. It's on page, actually it starts on page, I saw it just a second ago, 281. And I want you to do 1 through 27 odd. Okay, 1 through 27 on, starts on page 281. The bulk of it's on page 284 and 85. Ooh.